Next, we have Franz Luef, who is going to speak to us about duality theorems for shift-invariant systems and Green's imprimitivity. Franz.
Thank you, and I'd like to thank the organizers for inviting me, and it's a great pleasure to attend this conference. And yeah, so I was looking at this at the topics, and the only thing that comes close to what might be related to totally positive functions or things like this is this characterization that Charlie was talking about in his talk about Java frames for totally positive functions. And so he uses this characterization in terms of this Ron-Shen matrices. And during the past 2 years, together with Ulrich Enster from Oslo, we developed like a very general setup where you get type Ron-Shen type results, and they are, as we realized, consequences of a theorem that goes back to, in some cases, to Riefel from the 70s, and his student Phil Green in the early 80s, which is it's called imprimitivity theorems, going back to the work of Mackey on induced representations from the 40s and 50s. But I will not really tell you what the Green primitive theorem is. I will tell you the consequences because it's way too much operator algebras to tell you about. So this is a very representation theoretic approach that I will present you. So before I can do that, I will try to tell you my point of view towards Java frames, which is a little bit different of what we have heard so far. So it's more based on what's called C-star modules, which is this natural common generalization of filter spaces to a setting that's very useful for operator algebras. So, and for this, first of all, I need a nice function, class of functions, which is called Gleichninger's algebra. This space of all functions in, let's say L2, for which the short-term Fourier transform is in L1. Or let's say the Gaussian. Or any Schwarz function. It also comes with a nice norm, so this is space of all. This is also the norm of the space, and you can show that it does not depend on the G. And it behaves very nicely with respect to harmonic analysis things. It's Fourier invariant, you can restrict the subgroups, the closed subgroups, and so on. And for example, Marcus mentioned like the triangle function. That's an example of an object that's in here. So it's just like the indicator function of an interval that's not in there, but otherwise everything else is in there. That's a very mild assumption, but it has turned out to be very useful for Java analysis. So we have seen Java frames. Let's stick to this setting that we had before, that we take rectangular lattices given by alpha and beta as lattice parameters, and we look at systems of this type. And we assume for this talk that our Java atom is in this class as 0. And then we look at this analysis operator associated with. And you have seen that sequence you this superposition of frequency shifted versions G
Synthesis.
Mm.
Synthesis of.
Oh, sorry, synthesis. Yeah, I said we generate a new function based on our system. So in the time frequency point of view, it's like you take this system of functions and you take linear combinations of the system functions. But I would like to think about this a little bit differently. I would like to think of it as this operator acting on G. So this is actually call this A. A acts G. And let's see when this makes sense. So for example, we will restrict ourselves to A, B, and L1. And it's really just a linear combination of AKLs. So very nice, absolutely converging sum of time frequency shifts coming from this lattice. And so if you look at this, then so A going to this linear combination is really then just saying that go back to the classical analysis point of view. If you do this for L1 and look for corresponding convolution algebra, that this is some kind of extension of this kind of concept to this kind of framework. So this sum over AKL pi alpha k beta L give you a nice representation of L1 of Z2. But as you've also heard from Marcus, these guys are not commuting with each other. So this he didn't say it, but these guys generate a projective representation of the lattice. So you end up with carrying around this phase vector. So this what's called a twisted groups algebra, as a group algebra. So we get a representation of the twisted groups algebra L1 of Z alpha Z times beta Z. So let's write this. So we are actually looking at twisted. C is this phase vector that comes up when you compose two time frequency shifts. And you get C of so if you have no elements in here, then if you if you compose two of these and you do the same thing as you do for the case of sequences, then you have to do a shift of variables at one point, and then you have to take care of this vector when you have the position. So you get induced evolution on the sequences and some involutions, and they look like following. So we have twisted convolution. So you get some phase vector from exponential phase vector, and this makes it, of course, non-commutative. So twisted B and B twisted A are different. And you get an involution. Again, the standard one is decorated by a phase vector. So then, of course, when you now think about positive elements, it really means objects of the forum that are A star A. And so you have to remember that then if you have to take care of these phase vectors when you have to check positivity. Good. And then you can extend all of this associated C star algebra. So if you, one way of defining it would be, look at the operator closure of all this time frequency shifts from the lattice. This is by definition a C star algebra, but it has a name. It's called the non-commutative torus or a quantum torus. Or, and this is going to be important for us later, in this context, so known as the rotation algebra. It's called a cross product. And this object comes up in many different contexts, and it has, yeah, the structure is really also depending on this value of alpha times beta, usually called theta. But you have seen before, it's this area of the fundamental domain. And for example, yeah, from a representation point of view, if you want to study this kind of objects, and then rational is always the harder part and irrational is the easy part. So if irrationality here is your friend in this case. Good. Why am I doing this? Because there is a natural interpretation of Gauss frames as certain modules over over a non-curved torus. So we have, which is called Heisenberg modules. Going back to Kohn, as it was the first example of a non-commutative manifold. And then also reflate. The reason why it's called Heisenberg modules because its time frequency shifts are also a representation of the Heisenberg group. So the motivation is you want to construct the analog of a vector bundle for this kind of objects, and you think of these. So if alpha beta is an integer, then you have no commutation relations. Then it's just the continuous functions on the torus. So you think of this and for general parameters as generalizations of the continuous functions over the torus. So in the rational case, you end up with vector bundles over the space of continuous functions of the torus, as we have seen concretely in Charlie's talk. But you can do this also in general, doesn't matter if it's rational or irrational. And so what you do is, so you take your G as 0, so f and G as 0, and you define it like you usually do, like for Hilbert spaces, you define it for a nice class, and then you complete it. So we define it for fg in S0 and a in S, a some L1 sequence. Okay. And then we define an action as we had before. I mean, it's action we already had. Some AKL. And we also have an inner product. G left inner product. Where we take for this AKL the short-term Fourier transform restricted to this lattice. Since one of the features of this space is 0, that is in L1. This gives you an L1 sequence. And also this is again in S0. So this gives you really a action on S0. And this is really an inner product in the following, as we are used to it. So it's, if you interchange f and g, then it's the same as doing the adjoint of the original thing. And it's also positive. In this. And it's defined in terms of operators, so we know what positivity means. But it's positivity in this sense. And in our case, since everything is actually in a 0, I mean, this is positivity in this L1 sense. And we also have, if you take this action, which is, you think of as scalar multiplication, and it's same as, yeah, you can pull out the A, and then it acts on this inner product here. And if you find the following norm, then we'll take the operator norm of this element and take the square root. And if you complete now S0 with respect to this norm, then you get what's called E beta, and this is this Heisenberg module. And it turns out that, yeah, that's a theorem. In the case of Schwartz functions, this is due to one con. For a 0, I did it. So there always exists G1, Gn, such that any f is 0 can be written as f equals it. In other words, you can show that this is the same as saying we have seen Gauss frames for one window, but you can also do it for several windows. This is what's called a multi-window Gauss frame. And yeah, okay. And this is what's called rank 1 operators on this module, rank 1 operators. Yeah. Turns out that constructing these modules is the same as constructing these Gabo frames. And one thing one can also notice, like, so for example, if you have that, we have so far only heard about modules that have like one generator. So in this case, you have actually, you can show that constructing Gabo frames the same as constructing projections in this non-curved tori. And for C-star algebras, this is really non-trivial. So the first one who did this was Riefel in 1981. So in the case that you have that NEF can be written as FG G. This is the same as saying that you can construct projections, and you can actually do it explicitly. This is a projection. Beta. And this is in general, so in high dimensions, this is still not quite solved. So this is just in 1 dimension, in 2 dimensions. This is for C large was a highly non-trivial thing. And the advantage here is, so in many contexts, you need very much a lot of information about the P and to manipulate it. And so these totally positive functions are very useful in this context, and you can do computations. Good. Okay, that's so much for the motivation. So I already mentioned that in 1981, Riefel did construct projections. Data, but he used the description in terms of cross products. So this is the object, the operator algebraic object you associate to an action of a group on a C-star algebra, in our case, like the continuous functions on the circle. And that's also the link to this Ron-Shen matrices, because it really comes out of looking at these objects as cross products. So if you realize that it's a cross product thing, then there is these well-known theorems that allow you to give you a setting where this type of object appears, this kind of matrix. And one way to get there is, so we started with this description in terms of twisted group algebra. So we used the group as we think of the lattice alpha set, beta set as a group. And so now we want to get from this setting to this cross product setting. And the way is by just rewriting, for example, our action. So we had A acting on G. And I said, now I let my lattice to be alpha set times that. Well, I said beta equals 1. Otherwise, I would have here a beta. think of it in terms of sum over k g of t minus alpha k sum over L a k L t. And so this here is a partial Fourier transform, as a partial Fourier series where you just only use the exponentials that involve the L and have no k. So it's like a half a Fourier transform, so a partial Fourier transform. So we have AKT is exactly this expression. So you can think of this action now as having this GT minus alpha k times this partial Fourier transform, and this partial Fourier transform turns our operations that we had before, like this inner product and this action, into some very gives them a very nice form. So for example, you can look at what this inner product FG looks like in this context. So we take this partial Fourier transform and you just use the definition, and at one point you use Poisson, and in the end you get sum over L F B L G. And if we would have had like this beta here, we would have had here L over beta. So, yeah. I mean, I want to do the explicit computation, then it's a little bit cumbersome, but now that I just state the result, it's actually fine to do it this way. So we get here exactly this kind of thing that comes up in the matrix. And you can also do the same thing to this first product. Again, you just use the standard things about Fourier series, and you end up with sum over n. Minus m. So, and this is the convolution in this cross product. So this really is, yeah, exactly this kind of object. This is the product or the convolution product. Continuous functions on the circle. Oh, I have to write it this way. Not. By gamma. Gamma. That's this thing here. So in the case that we have this product structure, we can think of these objects as this cross products, and you also can rewrite the corresponding inner product and actions, and you get this kind of formulas that are used to study Galois frames in the setting. You get the Wallner representation, you get the standard things back. So this like gives you then also the rank one operator here, gives you the Wallner representation and so on. So in terms of like the tools that people use to study this kind of Gaba frames or those original Gaba frames, they come from this cross product structure. Good. Okay. So good. And let's see. Now it turns out that you can do this way more general than just for this two lattices that are so far involved. So if you look at things here, so we have one lattice lambda, which depends is alpha set, and one lattice generated constants 1 over beta. So we have two lattices that you are looking at, and we'll do it in the case where we have no Fourier transform. We do it for locally compact groups, but you can, I mean, easily either you think about the unitary matrices or you just think about R. Even in RD, it's interesting what's happening. So even many of the questions that you might want, like I've been thinking a little bit about it, how you would try to formulate at least what Charlie and Joachim have been doing for total positive functions in this setting. And then it becomes natural that, so the whole thing actually builds on this periodization trick that you can do this periodization trick in a very general way. So the standard thing is here. So we shift our, so we have this periodization of F by this lattice alpha set, and we can break it up into smaller pieces, and it all rests that we can decompose R into this translates of this interval 0 alpha, and in this case we also have the closed summation formula that we have already used and has been used before a lot in this kind of context. And you get like this duality theory is again closed summation, but there is a very general version of this where you take as a nice locally compact group, because we want that L2 of G is separable, so we add second counterpart. This is just sake of generalization, and then we look at a lattice gamma in G, which means that G is modular, so we don't have to worry about left and right things. And then one can show that there exists a nice finite G invariant probability measure on the quotient G mod gamma. So we look at this left closets, and then we have again because when you properly normalize the mu. So this is like the most general version, and for the setting that we were now in, this version before was sufficient. So I was looking at how can you get from, how far can you go from just using this. And the key thing was after a lot of staring at the formulas, we got like realizing that this is actually a decomposition of the space L2 of G into decompositions of little L2s where we have just translated versions. And so formally speaking, it's direct integral. So this natural extension of direct sums of Hilbert spaces where you replace a discrete measure on the integers by an arbitrary measure space. So, and it comes up, I mean, it was introduced by von Neumann because he wanted to do spectral theorem. So we needed to break up the space in smaller space, Hilbert space on the smaller spaces. So, and that's the key for like understanding this characterization is like really realizing that it's all about breaking up the L2 space into this little L2s. So we have this, so a collection of Hilbert spaces indexed by X over some space X. In our case, it's going to be measure space. And we have the corresponding, you will binomialize the inner product for the Hilbert space. And then you can also introduce the kind of measurability condition as like you would do for any Hilbert space, as any kind of measure-based situation. So it's not so important, we cannot go into details, but it's just important that we can associate to a family of Hilbert spaces a nice direct sum, as of which we call the direct integral. Here are the inner products, here's the inner products in each form. And we call it integrable when there's norm here, integrable with the norm that affects the grid of x. That's the x is finite. And of course, we have now that this direct integral is now a set of equivalence classes of integrable sections under this almost everywhere condition. But you can show this as under tools. It's like, yeah, you break up your Hilbert space into smaller pieces that you can handle better. And you also have the associated notions of like what it means to be a bounded operator and things like this. So let's look at this. So we have now this, let's say, two fields of Hilbert spaces. And an operator here is now, of course, now an operator that acts on each fiber, Tx, and we assume that it's bounded for each x. So this induces now a nice mapping, again, fiber-wise. And it's bounded. Oh, there's a soup missing. This, if the supremum over all the x of this norms of Tx for the individual hx to kx is finite. So we have bounded linear maps of this form are called decomposable because they have this structure that they're broken up into smaller pieces that only act on each fiber. And you also have a notion of positivity. So that this operator's form is positive, it's positive with each fiber. So this is one of the key things. You need to know like when it's positive. And so then you can define self-adjointness and positivity as before. And then it again boils down that you have to do it fiber-wise. So for each x or almost every x, you can do things. So it makes sense also to think about how to extend how objects like frames or real sequences look in this context. So we have a sequence Gj in our direct integral we call the fibered frame, or a real sequence if we have bounds such that the corresponding objects, when you now look at this Gjx and J, oh, that's not it. It satisfies the corresponding norms. I don't know why it doesn't display. So it satisfies the norm bounds and inequality bounds as before for the Hilbert space case. And you can define the corresponding analysis operations and synthesis operations, where again you now take f of so the Gx J now depends on again on the fiber. So for each fiber you do this, and then you take them together, and you do the same thing for the synthesis operation. You do everything fiber-wise, so that's why we call it fiber. I don't know if this has been done before or and the interesting and you also can define so now you have this synthesis operation which consists of the c-axis and the corresponding adjoint operator, which is the utterly analysis and synthesis operator. So the composition of these two is called the frame operator. We've seen this before, but now we do this in each fiber. And if you do it CC star, then you get the ground matrix. And so we have that such a sequence is a fibered frame satisfying this type of condition precisely when it satisfies the resequence condition for the space edge A. Because the spectrum is the same, except for multiplicity of 0. But we assume it's invertible, so the 0 doesn't hurt us. Good. And as before, you define the notion of dual frames and so on, and biorthogonal sequences where the inner product of these two are just delta. So so for a real sequence, you can talk about biorthogonal sequence. And it just satisfies all those conditions as in the standard case, but just now fiber-wise. Good. So now let's come back to our example. Where do we define? Okay, I define L on the next slide. Okay. So since we are in the setting where we have no commutativity, we have to be careful with left and right translations. So here I define left translations by f lambda minus x and right translations by r gamma f. So this is fx gamma for lambda in our lattice lambda and for gamma in our lattice gamma. And we have that this is a 5-bit frame, and if you write it out, it really is this type of condition where we have now, and now we have to be careful about in which order we take things. So in the abelian case, as we had like at the beginning, we were writing this as x plus gamma plus lambda inverse, but now we have to be careful and write this lambda inverse x gamma. So this is the condition for being a frame when we have this type of decomposition. So it's like, so as expected, so there's some little L2 condition on the G, but it's on the translates from each lattice, one from the left and one from the right. And the same for the Rees sequence. And note that the order of summation is interchanged, otherwise it's the same, and also the conjugation. But so this has the hold for every coset. And this looks very much like already what we had seen before in this sampling matrix or one-chain matrices, because we have now this kind of G lambda inverse x gamma, sum over A gamma, and that's the hold for all translates. The type of situation, and you can do the same thing for the right translations. So the action from gamma, and this is it indicates that there is a say the main consequence of this theorem by Green's imprimitivity theorem somehow tells you that these two actions that you have give you objects, C-star algebras that behave, that from a representation point of view are actually the same thing. So the representation, the category of representations that come with it are in one-to-one correspondence. So this is like this numerical equivalence of C-star algebras. And so and this we have noticed that as soon as we have this kind of nice notion of where these two C-star algebras have this property, then you always have like duality theorems. This I have done before. So, and then if you take now this general object, and in our situation we have traces and so on, then you can associate to it some Hilbert spaces, and that's what you get out of it. So it's exactly this kind of 5-bit frame situation. In the literature, you never see it written down this. They just write some cross product terms in that are appearing in this context. But it's, if you really write it out in terms of this L2 decomposition into this little L2s, and it really becomes this. So we have a 5-bit frame of left translates precisely when the dual objects are now the right translates of gamma, giving you a resequence. And so here you see that we didn't need like that. This second object here has like comes from is related to the first one. This holds for arbitrary lattices lambda and gamma. So there's not like lambda per, because we don't have this here, but it's like very general. So we can have any kind of lattices acting on this, and we still have this duality. So we have frame dual to Rees by just one time looking at like the left translates and the other time looking at the right translates. And then you can of course write down duality conditions in these terms, and also what it means to be a biformal system. And there's a this goes back to Riefel's work in 1981, which is like one of the, so at the very last page, there is like one footnote which implies this density theorem that we had, so incompleteness theorem that we had for. So this type of density conditions, but he actually studied something very more general. So he studied lattices in Lie groups, and they had to be certain, they have to be nice. Will explain what it means to be here, but there's a class of Lie groups for which you can really compute everything that you need to get density theorems. You have to do, but also know further about this, you have to be able to relate the coupling dimension of certain phenomenon modules of phenomenon algebras, and which in our case really boil down to the following. So if you have that the left translator are a frame, then the co-volume of gamma has to be less than equal to the co-volume of lambda for arbitrarily gamma. And this
concreteness, like, can you give some examples of the Lie groups which work with?
That's a good question. Yeah.
They're not simple because
No.
they have some radical.
Yes.
And they'd be just like, so is Rn, for example, under addition?
Yeah. Rn is fine.
Rn is fine.
Yes.
That is a concrete Lie group.
Rn is fine.
And non-abelian.
Yeah. There is definitely an.
Are there compact ones, for example? No, compact may not be simple.
I don't. Sorry. So you get also for the re-spaces condensed direction, the other direction. So that's like the most general thing you get out of this 1981 paper. But it's again not written in this way. He doesn't use the distinct positions, but he uses this cross products. But he uses this in a very way. But what it's really boils down to, I was talking about cross products over there, and I try to not really define it in general. I just tell you how it looks like for sufficiently nice functions. So let's look at compactly supported functions on this space, lambda times g mod gamma and lambda times gamma acting on lambda mod g. So of course, so the analogs of the formulas we had down there is like we take a lambda and the coset of x gamma and we multiply with f lambda inverse x, and the same for the other. So b gamma lambda x f x gamma for some L1 sequences in the space. And then you can show that the fiber synthesis operator that, for example, comes along with this left translates is of this type. So a lambda x gamma, g lambda inverse x. So it's like one way of representing this cross product structure. Yeah, and so you can do this for the left action and for the right action. So if you would do this more formally, then you would introduce the corresponding unitaries. And you can show that this satisfies all the properties that it's supposed to. And they also have like some nice substitutes of integrals. So the trace in this case is the substitute of the integral, and it really in this case consists of two parts, like one part integrating over this quotient, and the other is just the delta, like you would have in the standard case for the knockoff torus. So in short, these are like as nice as you can think of. Like in terms of non-commutative C-star algebras or phenomenal algebras or whatever, this is like the nicest thing you can get. And these actions, they commute and everything. I mean, it gives you this kind of equivalence bimodules and so on. So this is like why Riefel can do what he can do, because he has this way of like defining cross products and showing that they are Morita equivalent. And from this you get all this results. It's like the cross product version of this phenomenon algebra as a system module thing that I just told you about. And we can also go back to the Garber case. So if you have like a locally compact abelian group, let's say Rn, and you take a lattice gamma, then you have the dual group. Where,
The dual group is just the characters into
yes,
class.
the characters, yeah. Because it's abelian.
Yeah, yes.
And you also have a nice isomorphism between the Pontryagin dual of G mod gamma and the dual group. And again, the way to do is doing this partial Fourier transform. And so again, if you use this partial Fourier transform, it's just the version for this locally compact abelian setting. Then you can show that this phi of set gamma for this lattice lambda times gamma is a Gabo frame precisely when this condition is satisfied. But this is exactly the condition of this Ronchian matrices. So this has to hold for almost all X. I mean, this is exactly taking care of this decomposition into this relative spaces and all the cosets. And so if you look at this duality theorem that we had before, you can now think of like introducing shift invariant spaces associated with left translates of lambda and the right translates of gamma. And so this duality theorem tells you that you have either that X plus gamma is like a sampling set for V lambda, and only if the other thing is an interpolation set. So you have a very general duality theorem where you need, and this is now in general, you don't need any commutativity or anything. So this is like one consequence of this Green's imprimitivity theorem, is like gives you this general duality theorem. And also, I mean, I don't know, looking at this kind of characterizations over there. I mean, we have this this kind of G lambda inverse X gamma now for this locally compact groups. I mean, it would be interesting to see if you can, I mean, for example, one can definitely also do like this painless case that people have been doing. I mean, you can do like painless frames and construct some frames. And but definitely would be interesting to see if you put like conditions on like this totally positive condition minus for this. In the end, we just talk about lattices, so we have countably many points. So I don't know if people have looked at this at all. I only know that like I don't remember for which class of groups that Lustig did it, but at least for some groups there is a notion of total positivity.
Reductively.
Yeah. So I don't know. There is like now classes of frames where you can apply it to. Yeah. Thanks. This is it.
Okay, do we have any questions? I have a few.
Go to the slide with the one, I think it was 19 or something. Right, yeah. Oh, yeah, that's